Thanks a lot. So I'm very happy to be here at the school with you and to teach you about this exciting topic of effective field theory. It's a very broad topic, so I'm going to only be able to sort of scratch the surface, but my goal in these lectures is to give you an idea of some of the sort of most important things about effective field theory, some of the key things that show up in every effective field theory. I'll use specific examples to do that, and we'll see what those examples are. They won't all be particle physics. I'll try to give you some examples that are maybe atomic physics or other parts of physics, just to kind of show you that it's a broad tool that can be widely applicable. I have a course on effective field theory that I teach, and the course is actually available as an online course. And so in the Slack space, I posted a link to this online course, and you can use that as a reference for the material I'm teaching you about. So this course, the online course, which you see here, is a whole semester, and we will only be sort of covering little bits of it. But this also has in it some interesting things like a syllabus that has links to reading for the various topics. And there's also homework problems that I'll refer to in the course. And the homework problems are very nice because they are actually homework problems that you type in answers that are kind of latex strings, and the computer checks your answers for you. So you can get real feedback on whether you understand something. So I'll refer to problems in the course as I go as sort of ways that you might follow up on what we're talking about to learn more. Okay, so I'm going to start with some motivation for effective field theory, and part of that motivation will be describing to you kind of what it is, but it'll also be describing to you applications that we won't necessarily introduce in detail in the motivation, but then we'll come back to in later lectures and talk about what's going on in those examples. So it's really in the motivation, just giving you an idea of what kind of physics we can treat with effective field theory or why we want to do it. And this will take us a while because there's lots of good motivations for using effective field theory. So one motivation, which I don't even give a number to, is that every field theory is an effective field theory. And hopefully by the end of these lectures, you'll really understand why that's the case. Okay, so if every effective theory is an effective theory, then then we're always doing this. But there's, in particular cases, there's real applications in which it's more effective than others, and you're really thinking about the kind of expansions that go on when you're doing effective field theory. And so that's kind of what I'll be focusing on here in the motivation. So the first motivation is that we want, when we do effective field theory, to think about the simplest theory. Maybe not the most complete theory, but the simplest framework to describe the physics we're after. We're lazy. We don't want to work very hard if we don't have to, so we should think about what the simplest field theory is that we can describe the physics we're after, and not use something that is too complicated. Now, of course, we could use something that's too simple and then we get the answer wrong. So we really want to use the simplest theory that it captures the essential physics and doesn't leave out anything that's sort of essential, but things that are not essential we're allowed to leave out. That's kind of the heart of what effective field theory is about. And you're familiar with this because we do it all the time in physics. Whenever we teach a course in physics, we're always leaving something out. So let me give you an example that you're all familiar with. When you're taught the hydrogen atom or hydrogen-like atoms in quantum mechanics, you write down a Hamiltonian, and you write p squared over 2 times the mass of the electron, and say there's a Coulomb interaction. Maybe it's not a simple hydrogen atom, but maybe it's an ion that's been stripped of all but 1 electron. So there's some nuclear charge Z, just to make it a little more complicated than a simple hydrogen atom. So you have a Hamiltonian, you have a Coulomb potential, a kinetic energy term, and then you go and you run with it and you solve it. As you know, we can solve this problem. One of the few problems in physics that we can solve exactly. But there's a lot that's left out of this equation. There's a lot of approximations that have already gone into the system when we write that down. So one of them is that, where's the proton? It's not, you don't really see it in the equation. Well, the proton is acting as a source of charge. It's sitting at r equals 0. and you've treated it like a point. So I'll make some list of approximations that we've made for this equation. So the one is that the proton is a point particle. There's no structure to it. It's treated as if it has 0 radius. We neglect its size. We've also neglected the proton mass. Effectively, you can think of the proton mass as being sent to infinity. And what happens when you do that is that the proton is so heavy that it can't recoil, and it just sits in one position. We might as well pick it to be the origin. And it acts like a source of charge. It's charge plus 1 for the rest of the system. So those approximations are in the background. Another approximation that we've made is that the electron is non-relativistic. This is showing up in a course on non-relativistic quantum mechanics, and the electron is non-relativistic. We've written down a non-relativistic kinetic term, not the relativistic energy of the electron. And there's all sorts of things we've left out. There's no quarks in this thing. The proton is treated as a point particle. We don't look inside it. There's no quark masses. There's no other masses from the standard model. There's no mass like MB, MW, etc. All these things are things that are not part of the theory. So we've made some approximations in order to do that, to write down that Hamiltonian as a 0th order description of the problem. And if we were to go to higher precision, then these things would start to become important. Okay, when you start talking about the hyperfine splitting, then the proton mass is important. You have a spin interaction involving the spin of the proton. You could go to cases where the charge radius of the proton eventually comes in. You know, relativistic corrections, you can include those. So all these things are things that you can correct for, even these things too. But they're not part of the leading order description, but yet this is a very nice way of doing the computation because everything is tractable and you get the essential physics in that Hamiltonian. Okay? So that's a good motivation because doing the calculation with that Hamiltonian rather than using, say, the full standard model, if you tried to calculate the hydrogen atom with the full standard model Lagrangian, it would be a mess. And you would end up making approximations that lead you to this equation. If you have comments or thoughts or questions, please just raise your hand, or if I'm not paying attention, just say, I have a question. Okay, so the real thing that effective field theory is good for is that it separates the physics at different length scales. And that's kind of what is in part going on in this thing that I labeled A. So there's different mass scales in a problem or different energy scales, and effective field theory is separating those scales for you. So in this above example, you can think of it, the scales in the problem is there's some momentum of the electrons, and that momentum is actually of order the mass of the electron times the fine structure constant, and it's much less than the mass of the electron, and that's why the system is non-relativistic, because it has small momentum compared to the mass, and the mass is a heavy scale. And then the mass of the electron, again, is much less than the proton mass. We can think of the proton mass as being infinitely heavy. So we're making these expansions, and that's why we're led to that Hamiltonian. We're separating the physics at these different scales, and then we can focus on the lowest energy physics, which is what the effective field theory is aiming to do. Let me give you another example, a more particle physics type example, but a classic one. When we do the standard model for weak interactions, we have transitions between quarks of different flavor. Bottom quark can change the charm quark, etc. Up quarks and down quarks can change. And that happens through W exchange, but the W is a very heavy particle. So here I've written mass of the bottom quark, mass of the charm quark. This is like 5 GeV, this is like 1.5 GeV, and this is 80 GeV, much bigger. So we can expand with the mass of the bottom and the mass of the charm being much less than MW. And that means that we're doing an expansion in something that I'll kind of generically call W, or delta, sorry. We're making an expansion in this ratio, saying it's much less than 1, and we're organizing things in terms of this delta parameter. We can take delta and expand in it. And this is the classic Fermi EFT, Fermi Hamiltonian. We can organize the theory, meaning the Lagrangian, as an expansion in delta. So you could think of it as generically, if there's some delta, we have a series in the Lagrangian where each term in the Lagrangian is a certain order in whatever my power counting parameter is. So this delta is going to be what people call a power counting parameter. And my notation is that L with superscript k is of order delta to the power k. So smaller by 1 delta from the previous order. So in this case, we sort of have a physical scenario that looks like this, where bottom and charm are much less than the mass of the W in some plot of energy or mass. And if you think about, so you could think about what is this theory, okay? So far I've just sort of described it generically. And this is pretty simple. You can think about the Feynman diagram, say, that involves a transition from bottom to charm. And just for simplicity, let's let these be neutrino and electron. We have some different choices. So there's a diagram that has an explicit W in it. We haven't expanded yet. But in the kinematics of the process, all these external particles have momenta that are down near this scale. The physical process, the bottom quark is decaying, say, to charm antineutrino electron. And so that's happening at the bottom scale. So the momentum in the process, the momenta that are released to the final state particles, it's all going to be small. So the external particles have small momentum, and then you have this very heavy thing being exchanged. And so that means that if you think about the W propagator, there's some momentum k, but the momentum k of the W is just, of course, the difference of external momenta. And so that momentum k is going to be small. And we can neglect the momentum k relative to the mw squared. That's what's happening for the expansion here. And we just replace the propagator by, in this case, minus 1 over mw squared. And if you think about physically what's happening when I do that, it's making the W into a point. Okay, it's no longer, we don't see sort of anything propagating, we just see a contact interaction. And that's what this Fermi theory is. So we're led to a Lagrangian, which is for the Fermi theory. Sometimes people write it as a Hamiltonian, but the difference is just a minus sign, so it's classically written like this. P left is a left-handed projector, so that everything is a left-handed particle, and that's because the W connects to left-handed particles in the standard model. These are fermionic fields, just denoted by their identity, whether they're electron, bottom quark, charm, or neutrino. There's some coefficient, and when Fermi wrote this down, he didn't know about the W bosons, so he wrote this down as an effective model, and it described the physics, and he called the coefficient this. So this is historical, why the coefficient is written like this. From this calculation over here, you can actually figure out that the coefficient is just related to the properties of the W boson. So this coefficient is the electroweak charge, which I call G2, and then there's a 1 over mw squared from this propagator, okay? And this is this contact interaction. So instead of describing the Feynman diagram like that, we've shrunk the W to a point, and we have a 4 fermion operator that looks like this as the lowest order term. So it's a local operator, as opposed to the operator over here where there's something propagating in between, okay? And that makes things a lot simpler, actually. If you want to calculate the physics of B-quark decays or B-quark physics, working with Hamiltonians like this one or Lagrangians like this one's a lot simpler than having propagating W bosons. So calculations get easier. And that's a main motivation. If you want to think about why the calculations are easier, you could just think about the fact that, this is only the starting point. I'm going to start calculating some loop diagrams. And maybe I'm going to start adding to my local operator. I might add a gluon, like that, if I wanted to do loop calculations, right? And you can compare that type of loop calculation to what you would have if the W boson was propagating, right? And this is a box diagram. There's 4 propagators, and this is a triangle diagram. The triangle diagram is easier than a box diagram. Plus, it's not just that. There's more scales in the loop integral here, because the W scale can come in as a dynamical scale in the loop integral. Whereas here, there's no W mass in the loop, so you can't get answers that depend on the W mass. And that also makes even the sort of nature of this loop integral, which has one less scale, to be much, much simpler. Okay, so really the calculations are really getting a lot simpler. So organizing the calculations in this fashion is very efficient and very, very nice. Any questions so far? Well, that brings me to my next example. Yes, so it's possible that, okay, so I'll give you a very simple example. The QCD Lagrangian is very simple. We can write it down in one line. And every effective field theory that we derive from it is more complicated. But that doesn't mean it's not worth doing. So like just the fact that the Lagrangian looks simpler, it doesn't necessarily mean that the calculations are going to be simpler or easier. That's sort of the heart of it. Yeah. So the Lagrangian itself is sort of not representative of what you end up finding when you dig in. Yep. Let me give you one more example. This example here, the reason I give you one more example is that this example here makes it seem like this is just about massive particles, heavy things. We are talking about masses in this other example as well. So is it always about masses? No, it's not always about masses. So let me give you one more example that is not about masses. Where there's no masses, everything is massless. Let's imagine we have a process where there's a large momentum transfer. So this could be like a process in the colliders that you were hearing about this morning in lectures, where you're colliding 2 particles at very high energy. And if we did that, so let's say we had some particle coming in this way, some particle coming in this way, very high energy, and then we get a lot of momentum transfer. So maybe there's a gluon, and we get 2 particles at large transverse momentum that are kicked out into the main detector. So there's some Q here, momentum transfer, and I'm going to imagine that that momentum transfer is large. Q squared, much bigger than all the invariant masses of all the particles, so P1, P2, P3, P4 for the external particles. All the P's are, of those individual particles, the P squareds are small, but compared to this momentum transfer that's happening in this process. So in this case too, even though it doesn't seem like it, or even though it seems like it's more complicated than the masses, because Q is a momentum, and it can change. Like the mass is a fixed quantity, but the Q could change depending on the collider setup, for example, or depending on the kinematics of the process you probe. Even though that's the case, you still have a sense in which the process at long distance looks much more local than it does, because at long distance, at low momenta, you don't see this propagator of the Q squared. So even in this case, at low momenta, that shrinks to a point for the long distance part of the process, with sort of a 1 over Q squared instead of a 1 over MW squared. Okay. I'm going to come back to this probably in my last lecture. We'll talk more about the effective field theory of this. But this is just a teaser in a sense to tell you that things can not just involve mass scales, although those are the most sort of common examples that we treat with effective field theory. So the key principle here, if I want to sort of summarize what we've been talking about, is that you can really focus on the physics of the low energy scales without worrying about the physics of the high energy scales. So if you want to study the physics at some small scale, which I'll just call little m, just to give it a name, little m squared, then we do not need to know the details of what's going on at higher energy scales. In particular, we don't need to know the detailed dynamics at scales that are much bigger than this little m. And that's why Fermi was able to just write down his Hamiltonian or Lagrangian and actually make predictions without knowing about the W bosons. Okay. Of course, there's some benefits of knowing about the W bosons. We'll talk about what those benefits are. But this key principle is why we're able to use effective field theory and organize the physics in this fashion. And of course, this key principle is what won Ken Wilson the Nobel Prize back in '82. The fact that the physics, even including renormalization, can be separated in this fashion. Any questions? Okay. Well, I'm not done. I think I'm on B. We're going to keep going. So the list will go on for a while. Well, you might say this is all well and good, but you've dropped some physics, right? You made this expansion, you left something out. And the point is that the idea of the effective field theory is that you don't want to think of leaving anything out. You want to just think of focusing on the physics that's most important and adding the physics back that you've left out systematically, order by order in this expansion. Okay? So you keep precision by just going to higher orders in your expansion. The expansion is in this delta. And if I'm interested in a baseline prediction, if I'm expanding in, say, a tenth, and I want 10% predictions, then maybe the leading order effective field theory is good enough. But then, if I want 1% precision, then I need to go to higher orders. But there's a systematic way of doing that in effective field theory, and so we don't think we've given anything up. We just think we've neglected things and left them for later, is the idea. Of course, actually doing that can be complicated. And so as you go to higher and higher orders in the expansion, you're going to get more and more terms in the Lagrangian, and more complicated stuff can happen. And so there's maybe some practical limitations to doing that. But usually the practical limitations kind of align with the experimental limitations as well, because experiments are never infinitely precise either. And so organizing the things in this way is always sort of still beneficial. Okay, let me keep going. D. This one is one that sort of, this item is something that we know is very nice about quantum field theory, is that we can really make a lot of progress just by exploiting the symmetries of the quantum field theory. And in effective field theories, it's the same thing. Now, the thing that's different about effective field theories is that there could be some approximate symmetries. So they might not be exact symmetries of the full theory, they might be approximate. But if they're approximate in a way where the subleading things that are breaking the symmetry are small, then we can have an approximate symmetry that's, say, of the leading order Lagrangian that then it gets broken only by higher orders. So symmetry of L0 broken by L1 is sort of a common situation. And that's what I mean by approximate. Or even emergent. What does emergent mean? Emergent means you stare at the theory before making any expansions and there's like no sign of the symmetry. Okay, it just doesn't look like it has a symmetry at all. Then you do the expansion, you get some effective Lagrangian, and you study that effective Lagrangian, you say, lo and behold, there's a new symmetry that you didn't expect that showed up. Okay, so that's very nice and beautiful, and then you can go to town making predictions with that. So I'll give you a couple of examples. I'm not going to define the theories in full, but just give you some examples that you may have heard of. So one example is chiral perturbation theory in QCD. So this is a theory where your degrees of freedom are things like the pion, the proton, etc. And you're interested in very low momentum interactions. You're interested in interactions that are at scales that are much below lambda QCD, or what's called the chiral symmetry breaking scale, lambda chi. So very small momenta. The pion mass is also very small, and it's part of this program. And the symmetry here is that there's a spontaneously broken symmetry, which is the chiral symmetry of QCD, that plays a crucial role, and these pions are Goldstone bosons of that symmetry breaking. There's also an explicit breaking because of the up and down quark masses, for example, that give masses to the pion. And so there's different kinds of symmetries that are broken in a particular way that the theory sort of builds in and describes. And you can go to systematically and expand in that. Another example, and this is an example of this second category of emergent symmetries, is what's called heavy quark effective theory. So if you like, this is a theory of light quarks. Now what about heavy quarks? Well, the ones that are applicable here are the bottom and the charm. So if we take bottom quarks and charm quarks, then we can note that the masses of a bottom quark and a charm quark are actually quite a bit bigger than the confinement scale of QCD, the scale where QCD gets strong, which I denote as lambda QCD. So we can think about that kind of expansion. The physics of hadronization is happening at this lambda QCD scale. And then there's this like heavy particle like a bottom quark that might be sitting inside some hadron that's built out of a bottom quark, for example, and some light quark. So typically this is applied to things like bound states of a bottom quark and a light quark, or a charm quark and a light quark. So I'm denoting the light quark by a little q. And this theory actually has an emergent symmetry. When I take this limit that the bottom quark and the charm quark both get heavy, bottom quarks and charm quarks look the same because they're both heavy. If they both are infinite, I can't tell them apart. So there's an extra flavor symmetry between bottom and charm in that limit. And it gets even better than that because there's also a spin symmetry. So there's what's called a spin flavor symmetry that emerges, where bottom quarks that are up, bottom quarks that are spin down, charm quarks that are spin up, and charm quarks that are spin down all behave the same and get related by the symmetry. And that symmetry is not there in QCD. In QCD, we have the sort of Dirac Lagrangian psi bar d slash psi. D slash has a gamma matrix in it. Okay, there's no sign of a spin symmetry there. And bottom quarks and charm quarks have a different mass term, mb psi bar psi or m charm psi bar psi. So there's no, and they're quite different. You know, mb or m charm over mb is like mb over m charm is like a 3, factor of 3. But if I think about them going to infinity, much bigger than some other scale, then there's this symmetry that emerges. Okay. And you can use it, and it's very powerful. Pause and drink some water and see if anyone has a question. Okay. Kind of connected to this, and these things that I've mentioned so far, and it's a very powerful thing that we use effective field theory for, is that we can include non-perturbative effects. So it's not just about perturbation theory. I've sort of been thinking about it as perturbation theory in some of the examples that I've given when I drew a Feynman diagram as perturbation theory. But we can also include non-perturbative effects in the effective field theory, and it kind of happens naturally. So for example, if I'm thinking about QCD, QCD has a running coupling, and the coupling in some regions of parameter space is large, and in some regions of parameter space is small. So if I have two scales in the problem, say I have a scale Q that's very big, and then I have some kind of scale, maybe it's a rho mass, and it's very small, of order this confinement scale, then naturally there's couplings at Q and there's couplings at this M rho, and the couplings at Q are going to be perturbative. Alpha of Q is small, and the couplings down at M rho are big. Okay, I'll just say they're order 1. So there's perturbative physics and non-perturbative physics simultaneously in the problem, and just by separating the scales, you can figure out which of what the physics is that's non-perturbative and what the physics is that's perturbative. And the nice thing is that this non-perturbative physics, which is the physics of the low energy theory in this case, can be universal. So in this heavy quark effective theory, for example, I'll just give you an example of something, of some universal parameter that shows up. So I don't describe for you where it comes from, but there's some matrix element called lambda 1. It's a matrix element of between two B quarks of a D squared term, and it kind of behaves like a kinetic energy. It's probing the kinetic energy of a B quark inside a B meson. This is a universal parameter. It's a non-perturbative parameter. If you go through the dimensions, you find that it's of order lambda QCD squared. But the effective field theory has this matrix element show up all the time. So even though we can't calculate that matrix element, maybe we can calculate it on the lattice and with some non-perturbative methods, but we certainly can't calculate it in perturbation theory. Even though we can't calculate it, it doesn't really matter. It doesn't bother us, because if this parameter shows up in multiple different places in multiple different observables, then I can measure it in one place, and then I can use it everywhere else. Okay, so it's powerful because it's classifying the non-perturbative effects in terms of a certain number of universal parameters. Okay, I think we're on F. So another thing that happens that effective field theory is good for, and you may have heard of this, is summing large logs. So it turns out that when you have a scale separation, like the ones I've been talking about, that if there's two scales in the problem, there's inevitably going to be logs of ratios of those scales that show up. So in this example where we had a bottom quark and the W mass, there would be logs of MW over MB. And there's a series that look like this with some coefficients A. And these logs, being large logs, MW is much bigger than MB, kind of compensate for the smallness of the alpha, right? So if you multiply alpha by a big enough number, then this thing is order 1. And you have to sum up these logs, but the effective field theory allows you to do that. And the way that that happens is very natural. It's by the renormalization of the effective theory. It sort of automatically handles these logarithms, or more technically, you could say it's because of the renormalization group evolution. So renormalization and renormalization group are connected concepts. Sometimes we abbreviate this by RGE for renormalization group equations, or renormalization group evolution. And the thing you sort of need to calculate are what's called anomalous dimensions. These are analogs of the beta function in QCD, but sort of generalized to your EFT. And I'll talk about examples of this, so I'm just mentioning some words here. If they don't sound familiar to you, that's okay. But the point is that we can handle these types of logs and calculate these A's, and it's not so hard. And when we can sum up the whole series, then that's not so hard. Another way of thinking about why that's important, just to get a little bit of a feel for it, is just looking at the strong coupling. And you could say, well, if I've got a problem that has MWs in it and MBs in it, which coupling should I use? Should I use the coupling at MW? Okay, remember the coupling changes with scale. Should I use the coupling at MW or the coupling at MB? Well, the coupling at MW is about 0.1 and the coupling at MB is about 0.2, so it kind of matters which you pick, right? They differ by a factor of 2. So which one should I be expanding in? And that question, the question of which one, is answered by doing this procedure. It tells you precisely which one you should be expanding in, because the difference in expanding in one versus the other is exactly a series of this sort. So if you have these series under control, you also have the answer to this question under control. So this gives you a little bit of a flavor for maybe how important summing that series is. Okay, so lots of good motivations. I still have at least one more. So my next motivation is that effective field theory can be a good way of understanding and characterizing new physics. It's kind of efficient at doing that. It seems at first glance that this kind of is a little bit of a strange statement, because isn't the new physics going to be heavy? Isn't that sort of going to be outside the range of my effective field theory if it's some heavy scale beyond the scales that I'm probing? But nevertheless, it's a true statement. And the idea, in this case, is that you can think of the standard model as the zeroth order term in an expansion of standard model scales. Your expansion is standard model mass scales, so I'll just call it MSM. This MSM could be the W mass, it could be the Higgs mass, it could be the top mass. MSM, standard model masses, over the scale of the new physics. So I am making an assumption that the scale of the new physics is high enough that I have an expansion parameter, and that this is small. But if that's the case, then I can organize things as a Taylor series in this ratio. And the new physics gets sort of integrated out into these, or removed from the theory, in the same sense as the W mass being expanded and removed from the theory. And it shows up as sort of the coefficients of these subleading terms in the Lagrangian. But the nice thing about this is that I don't have to tell you, if I want to sort of organize things this way, what the new physics is. I can just use sort of completeness and construct a complete set of Lagrangians that satisfy all the symmetries of the problem, independent of knowing anything about what new physics is, except that it's heavy. I have to know that the new physics is heavy. And then I can write down complete Lagrangians here that characterize that new physics, and I can try to constrain, say, the coefficients of those Lagrangians to look for new physics. And this is called in particle physics literature, the standard model EFT approach to looking for new physics, so SMEFT for short, and it's a very powerful technique. So let me just write what I said. We constrain the unknown parameters in L1 and L2 by data, and that puts constraints on new physics. And that doesn't preclude you from using those constraints to, maybe examine your favorite model. If you have a model and it has some heavy particles in it, say your model has only heavy particles in it, then you could figure out what your model predicts for these coefficients in the L1 and the L2. Okay, just like integrating the W boson out, expanding it out, you could do that same type of procedure in your model. And then you could compare to somebody else's analysis of this SMEFT and see if your model is, ruled out or ruled in. Is it still surviving, or is it constrained by those constraints? So even if you're, really attached to some particular model, this is still a useful way of thinking about how you might put constraints on your model if you have heavy particles. I've given this example kind of in a particle physics-y way, where I've said it about characterizing new physics, right? So this is like new physics beyond the standard model, high-scale physics, things that we're interested in probing when we build colliders to probe short distances. But the general idea here, this is sort of an example, the general idea of characterizing new physics by thinking about the subleading terms in the expansion, it goes beyond just the standard model. It applies to any case. If I was going back to the hydrogen example, the new physics there would have been like the spin-spin interactions or the hyperfine splittings or the Lamb shift, and I could characterize that physics by thinking about subleading terms in a Lagrangian, even if I didn't know necessarily how exactly to calculate it. So it's, again, a general principle being maybe maybe the most exciting application is this one, but like it's also a general principle. I'll add an H. So the way I've kind of described it to you, it sort of seems like maybe it's automatic, right? Like, oh, I just do it, and I get the effective theory, and life is good, and can relax, it's easy to calculate things. No. Sometimes you really do have to think when you're constructing the effective theory. It's easy to get, when you're figuring out what the effective theory should be, you might get it wrong at first. You might need some cross checks to actually figure out what your leading order theory is. Okay, so physics really does come in to thinking about how you design your effective field theory. Chiral perturbation theory is an example like that. Like, would you think that you're supposed to write it down in terms of the pions and not quarks? If you knew about them, you might not think that, but those are the right degrees of freedom. Other examples, like soft collinear effective theory, which is the effective theory for collider physics, has multiple kinds of gluons. It has soft gluons and collinear gluons. Would I have thought to do that right off the bat? Maybe not. So it has two different types of gluons that you have to have in the effective Lagrangian. Another thing that maybe is the most important one is that depending on what kind of experimental measurements you make, experimental measurements can produce new scales. There could be an experimental resolution. There could be some experimental cuts on the data. If you get new scales, that might mean you need a new effective field theory. So depending on exactly what is measured, the baseline might be that it's a certain process, but depending on exactly what the cuts are, the size of the scales that are introduced by those cuts, you might need to think about all that too when you're designing your effective field theory. And these things, all go under the category of that you better think. Okay, let me pause to see if there's questions. Okay, so how should we think? What are the kind of, is it just like, oh, it's a black box and you just have to think lofty thoughts and then figure out the EFT? Well, there are some procedures that you can go through in order to get going with how to construct the effective theory. And so it's not just a black box. There's some things that are common that you have to think through. And so I'll just tell you what those things are. They're kind of obvious, but let me nevertheless tell you. So to determine the effective theory, the first thing you need to figure out is what are the relevant degrees of freedom. Degrees of freedom is a very long phrase, so I will abbreviate it. DOF, degrees of freedom. And the relevant degrees of freedom are, of course, going to be the things that you write down quantum fields for. So this is answering the question, what fields does my effective Lagrangian even need to be built out of? Some fermion, some scalar, a gauge field, etc. What are the relevant degrees of freedom for the process that I'm studying? And that could be easy. It could be kind of obvious. I've got an electron. I never better have an electron field. It could be not obvious. Okay, so even this step, you might take some while to figure out, depending on how complicated your problem is. The next thing that I'm going to put in the list is symmetries, because the next question that you're going to ask once you have the fields is how are they going to interact with each other? And symmetries can eliminate interactions or relate interactions in the theory, so you have less terms. And so that's very, very important. Constrains what interactions are, maybe the interaction's not allowed by the symmetry, maybe some terms in the Lagrangian are connected, like gauge symmetry connects the partial derivative to the gauge field. So symmetries are very helpful. And then the third thing is what am I expanding in? And sometimes, that's also relevant to think about when you're answering the first question. But I should really be careful to enumerate all the things I'm expanding in and figure out what the leading order description is, because that's where I'm going to start. And this goes under the name of figuring out what my power counting is. This is my delta. There might be more than one delta. Maybe there's only one. You have a simple effective field theory. Maybe there's two deltas, etc. But that's a crucial step. And in some sense, it's not a less important step than the other ones. So you might say, oh, if I have a gauge theory, obviously gauge symmetry is more important than the power expansion. And I would say no. This is just as important to understanding what you're doing. Because if you don't understand this, you don't understand what your uncertainties are. How good is your effective field theory? If I don't know what I'm expanding in, then it's not good at all, because it just could be wrong. And if you have all this and it's sort of working, then you get an effective field theory. Yep. Yeah, you could. Yeah, absolutely. If you're aware, if maybe you saw some experiment, there was a symmetry, right? And you want to describe that experiment, yeah, you should think about an emergent symmetry. So it could work either way. You could say, depending on the situation, you could actually know something about a more complicated theory that you then expand explicitly and you find the symmetry. That would be the example of heavy quark effective theory is like that, because I know QCD and I can just literally take QCD, expand it in this limit, and I see the symmetry emerge. In other cases, you're not so lucky. And if there was some symmetry of the new physics, it might be related to relations between the coefficients in some subleading Lagrangians here. And you would discover it by, finding from experimental data that there was those relations, or maybe you would impose it and test it. Yeah, good question. Yep. Yeah. Right, right. So, yeah, so the strategy is to try to classify all the non-perturbative effects. And you're going to have quantum fields in the effective theory that live at the non-perturbative scale. You can't do perturbative calculations with them, but you can still classify what operators exist, and you can figure out what the most important operators are. And then you're going to get matrix elements of those operators, and those are going to be some non-perturbative parameters or maybe some non-perturbative functions. And the hope is that with that data, with that information, and then like maybe you'd build a model for the function, or you try some numbers for the parameters, or you ask your lattice friends to help, that you would be able to describe the data. Now, if things go wrong, which sometimes they do, there's lots of things that it could be. And it could be that you were wrong and you missed some term, right? And it could be that the experiment has an issue or it's normalized funny. So there's lots of things that could go wrong. And, part of doing physics is fighting those battles and figuring things out. Okay. Well, I've described things to you fairly generally, but if you've heard the words about effective field theory before, you may know that oftentimes power counting in effective field theory is actually just related to dimensionality. And I want to spend some time talking about that. Because if this is true, it makes things a lot easier. We don't have to work really hard to figure out sort of how to do the power counting. We just look at the dimensions of operators, and then we know how important they are. So it's very powerful. And this connection between power counting and operator dimensions, if you say to some layman on the street, I'm working on effective field theory, they'll say, oh, okay, so you're working out higher dimension operators in some theory. That's kind of the notion of effective field theory is wrapped around operator dimensions. It's not always the case. So sometimes operator dimensions are not the right way of doing the power counting in the effective theory, and we'll see some examples of that in later lectures. But today, I want to explain to you how this connection occurs. And to do that, let's just consider a simple Lagrangian. I'll just consider a scalar Lagrangian, so an action, S of phi, single scalar field. I'll work in dimensional regularization, or I'll work in d dimensions just to keep things general to start. We'll later specify that it's 4 dimensions, but let's start in d. And I'm just going to start writing down terms. To keep my Lagrangian sort of contained, I'll impose a Z2 symmetry, that phi should be able to go to minus phi, and that it doesn't change anything. So I won't write down a cubic term, but I'll write down a quartic term. I think in my notes I've got 2 different conventions for this Lagrangian, but we'll start with this one, which has got some combinatoric factors for the higher order terms. So I wrote down terms up to phi 6. So this is dimension 2, dimension 4. Dimension 2 times the mass squared makes 4 dimensions. 4 dimensions. This has 6 dimensions, so this tau better have some negative mass dimensions. Tau is some coupling that sits in front of this phi 6 term. So I've imposed phi goes to minus phi, and I've also imposed Lorentz invariance, so every derivative comes with a friend. The Lorentz indices are contracted. Now, so I claim that I've included all the terms that I need to include up to phi to the 6. But if you think about it for a minute, maybe you could think about something I left out that's dimension 6. Can someone think of an operator that's dimension 6 that I left out? Yeah, something like that. So I could have something, if I want to get dimension 6, it actually needs to be phi cubed. So I could have phi cubed del squared phi. That's a dimension 6 operator. I left it out. There's another one, because I don't have to have the 2 derivatives act on the same phi. I could have one derivative on one phi, one on another. So that's maybe the one you were thinking of. because it looks like this kinetic term. So there's two operators that I left out. So what about them? Why did I leave them out? Well, one thing that I can make use of when I write down the effective Lagrangian is that a total derivative term is going to be some kind of spatial integral at infinity, but infinity is really infinity here. And such terms are dropping out. I don't need to keep them. So I can drop a term like partial mu phi cubed partial mu phi. And if I take and expand that out, I'm going to get 3 phi squared partial mu phi. And then there's a term where the derivative just hits this, so it's phi cubed partial squared phi. And I'm saying I can set this combination to 0 because I can drop it. And that relates the two problems. Okay, so it's not really two different operators that I missed, but only one, because this one and this one are related by this total derivative, or if you like, by integration by parts. If I integrate by parts, I can relate these two. Okay, so there's really only one operator. So this sort of here reduces the problem. Let's say it reduces it to phi cubed partial squared phi. I haven't completely eliminated the problem, but I simplified the problem down to a single operator that I left out. But I claim that I'm allowed to leave that one out too. So why am I allowed to leave that one out? That's a little more tricky, and I'm going to come back to it at the end of this discussion. I claim that this operator is removable by a field redefinition. This is a kind of change of variable in my effective field theory, and it's allowed to do such changes, and I'm going to come back to it. We'll leave it aside and we'll just trust that what I'm telling you is true, and then I'll come back at the end and explain why. Okay, so this is our Lagrangian. We can study it. And let's look at the dimensions of things. So I'm going to denote the dimensions like this. So d dx with square brackets is the dimensions of this. And these are mass dimensions. X is a position, so this is dimension minus d. Dimension of a derivative is the same as the dimension of a momentum, so it's plus 1. We can just go through and enumerate things. In d dimensions, the dimension of the scalar field is d minus 2 over 2. So if d was 4, then this would be 1, but in other dimensions it's something else. And that's because the action is dimensionless. Maybe I should have started with that. Remember, the action goes into the path integral as like an e to the is, and it better be dimensionless, working in units where h bar is 1. Okay, so from just this term, knowing the derivatives, knowing this is dimensionless, I fix the dimension of the phi to balance things. Probably you've seen this before. Anyway, it's not so hard. The mass squared has dimension 2. The lambda in d dimensions has dimension 4 minus d. I just go through and I determine the dimensions of everything. The tau has dimension 6 minus 2d. I know the dimensions of all the parameters and all the terms in the action. So let's say we have, this is sort of the dimensionality. Let's say we take this effective field theory, and I'm just going to stop this up to dimension 6. And let's say we want to study it at long distances, which is the same as small momentum. That's what the effective field theory is supposed to do, right? Look at things at small momentum. And more explicitly, let's say we want to study a correlation function of scalar fields, some phi with some positions, x1 up to xn, at large x's. Long distances. Small momenta. Well, a nice way of sort of characterizing that is to do the following. Let's take all the x's, x1 up to xn, and just rescale them by a common parameter s. And that just defines some prime coordinates. And then I can take s to be large. S goes to infinity. And that makes all the x's simultaneously go large together. I'll think of S as something that has the dimensions of a coordinate. So that makes these x primes here dimensionless. And the dimension of the S is -1. Just a choice. So this S is kind of going to be analogous to our power counting parameter, or 1 over our power counting parameter, because it's going to infinity rather than 0. If I make this change a variable, then it's natural to think about what happens to this term here, for example, because I've changed this ddx. And if we change the structure of this term here, this is our kinetic term for our scalar field. If we get some weird factor that's not a half in front, then we've got a weirdly normalized kinetic term. And that's something that we don't like, because it makes the quantum field theory complicated to have weirdly normalized kinetic terms. So we always can change variable to absorb such a factor and make this term have a canonical normalization again. So that's what we do. We normalize the kinetic term. And in this case, we can change variable from phi of x to some other phi. There's some s's that need to get absorbed. And then we define a phi prime that's only a function of x prime. And that gets rid of the s factors in this kinetic term here. This s to the 2d minus 2 over 2 is exactly the dimensions of the phi. Okay, remember this is s has dimension -1, so that flips this, d minus 2 over 2, that's the dimension of the phi. So this is carrying all the dimensions out front, and this thing here is dimensionless. Again, it's a dimensionless function of a dimensionless variable. Okay, so we just go through and we do that. We get a new action that's a function of phi prime, and we have an integral over x prime. And we changed variables so that this first term just involves phi prime. And then when we go through the rest of the terms, we're going to see various s's appear. So we just go through this and do it systematically. Write everything in terms of phi prime now. And we get this action. It's the same theory. We haven't really done anything. We just change variables, right? But the advantage of this is that now, okay, if we're studying these sort of correlation functions of phi's at these different coordinates, which I'm now writing in terms of the prime variables, this is written as some kind of prefactor that involves these s's, not too important, just an overall scaling. And then a correlation function of the phi primes. And in the phi primes, we've removed all the s's, kinda, right? Like at least in the kinetic term, there was no s's at all. So we can really kind of think of this here, and I'm apologizing for writing it so close to the bottom of the board, but we can think of this correlation function here among these phi primes as something that's order 1 plus higher orders. So order 1 plus dot, dot, dot. And that's because we sort of have a kinetic term here that has no s's, and then we have like explicitly s's elsewhere, and we can categorize how important the terms are by their power of s. Okay. Now, the powers of s, if you sort of follow the procedure, they were just related to the dimensions of things. So it's not sort of too magical to imagine that if I let capital D be the dimension of some operator, so this is operator dimension, whichever operator I'm looking at, what we have actually found, if you go back and think about where those s's were, is we found that the operators came in as s to the d minus capital D. The little d came in because of the ddx becoming a ddx prime, and then the rest of the powers of s just came about from the structure of the operator, its dimension. They were just tracking its dimension. That's what the s's were doing. And so d, the dimension of the operator, determines the importance of the operator. The importance of the operator in this language is given by the power of s. How many s's it has tells me how important it is. And that's just, well, little d is fixed. I've fixed which theory I want to talk about. Maybe it's 4 dimensions, maybe it's 2 dimensions, 3 dimensions, 10 dimensions. All good. But once that's fixed, it's a really big D that tells me how important a given operator is. And that's just the operator dimension. Now, usually we don't do this with S, so I've gone through this procedure with S because I think it's intuitively giving you a picture. But usually people just don't bother with all this sort of thing and just look at the original Lagrangian and do the power counting originally just from that alone. And so if we go back to the original phi without going to phi prime, we can also set it up things up there. And the idea is that S was a position, and a position is like 1 over a momentum. And in the original theory, we want to think about momenta divided by some sort of scale lambda being small. And so each S is sort of being traded for a lambda. And so with the original phi, the statement is that the coefficients in the original Lagrangian scale like lambda to the little d minus capital D. Okay, this is sort of S is order 1 over p, which is sort of, if I stick in a lambda, sort of giving a lambda. So lambda and S are kind of the same, so it's lambda to the bit little d minus capital D. Okay, and so so we can go through and do some examples just to see that this formula kind of makes sense and see what it says. I'm erasing my Lagrangian, but we all remember it, maybe. Or took notes. So let's take little d equals 4. We're interested in 4 dimensions. And let's make a little table of operator dimension, d, and the coefficient. And so let's just start with the d equals 4 terms. At d equals 4, the only non-trivial coefficient was lambda. And that lambda is dimensionless in d equals 4. And it's a leading term. There's no suppression to it. And that's kind of intuitively what we would think. If I go to the d equals 6 term, this is the tau. And I stick in 6. Well, I have 4 minus 6 is 2. And this is saying that tau goes like 1 over lambda squared. And so it's subleading. It's small. The dimension 6 term is suppressed by the heavy mass scale, which is dominating the coefficient. Okay, that's in this notation. And I didn't write down d equals 8 or higher terms, but you can kind of intuitively see that I'm just going to get more and more powers of lambda downstairs that are compensating for the dimensions of the operator. The dimensions of the operator are kind of tracking the physics within the effective field theory. The dimensions of the operator are describing the dynamics in the effective theory. So those dimensions are related to the p's. And then the coefficients, which is encoding any kind of physics that I've integrated out, is got the new physics in it, or the high energy physics in it, short distance physics in it. And so all the coefficients have these lambdas in them. Okay? And this is where how the p over lambda expansion corresponds to kind of operator dimension divided by powers of lambda. Okay, and this is sort of the classic picture. You may have seen this before. I skipped d equals 2, so let's talk about d equals 2. Because if I plug in d equals 2 into this formula, I get 4 minus 2, which is lambda squared. And it seems to say the coefficient which I called m squared, in my power counting should be lambda squared. What do we think about that? We think that it's a problem. This is a problem. And the reason it's a problem is because if that was true, then we might as well just go home. Okay, well, it's the first lecture, so maybe not quite yet. But this is a problem because if this is the case, if the mass squared was of order lambda squared, then I shouldn't have written down, if phi had a mass of order lambda, then I shouldn't have written down phi to begin with. It's not like a valid field in the effective field theory if it's got such a heavy mass. It should have been removed with all the other stuff at the scale lambda. And so what am I going to do? I have to demand that this is not the case. I have to make m small, much smaller than lambda squared by choice in order to even have a starting point to set up the effective field theory that I'm talking about. Okay, that's a problem. So we demand that m is much less than lambda. And effectively what we demand is that m is the same size as other things, like the momenta that are characterized by the phi's, other scales in the problem. We say m's, little m's and phi, those are the same size, and they're both much less than lambda squared, capital lambda squared. We're just going to do that. Then everything's fine, and that kind of means that m squared counts the same as a phi, and instead of calling this dimension 2, we're actually kind of effectively calling it dimension 4. We're counting 2 for the m's and 2 for the phi's, and it makes it into a d equals 4, and it makes it into a leading term, and then everything is fine. Okay, we're kind of forced to do that. Of course, the Higgs fine-tuning problem, when you think about gut models, et cetera, is related to this issue. But from the point of view of the low energy theory, this is just like, in order to even get going, this has to be the case. Any questions about that? Okay. Okay, I still have some time. Good, I'm not too far behind. Okay, so the moral of this is operator dimensions map to the importance of a term. You can think of it as lambda counting, i.e. we just count dimensionality, and then there's some dimensions associated to the couplings. If I have higher dimension operators, I have to have dimension 4 because the action ddx in d equals 4 is dimension minus 4. The action is dimensionless, so things have to add up. And so if I have higher dimension operators, there's always going to be lambdas downstairs in their coefficient, and the counting just tracks those lambdas. Very easy. If you ask kind of what were the assumptions, well, there were some. One of the assumptions, which I will relax in a future lecture, is that we were thinking here of Lorentz invariant theory. And if we relax that assumption, actually, then this is not true. Some of this, what we just proved, would fail. And it doesn't mean you can't deal with such things. If you have a non-relativistic theory, for example, the counting is just a little different. And we'll talk about that. Any questions? Yep. Yeah, sure. So d equals 0 operator would be the cosmological constant. Yeah. And so we're going to... well, it's kind of a weird operator because there's no fields in it. It's just one. Yeah. So effectively, yes. Like if we're going to... Okay, luckily it has a small coefficient. if we're going to think about other operators that have dimension less than 4, this is a generic thing. So if I had something that was dimension 3 in some theory, like a fermion mass term, same story. I have to effectively think of it as expressed in order for things to be valid. Yeah. Okay, so there was this little caveat that I said I would fill in the hole for, so let's go back and do that. How did I get rid of that term that I dropped? So my claim, in the sense of the effective theory, meaning for small momentum, is that I can drop that term. And I've decided when I wrote down this part of my notes, it must have been the next day because I used a different normalization than I did in the other part of my notes. So sorry for that. I dropped all the factorials. But anyway, that doesn't really matter. So let me put that term in, the term I dropped, and let me give it a coefficient kappa. That's one Lagrangian. The one we worked with was a similar Lagrangian, but it didn't have that last term. And my claim is that these two Lagrangians give the same description of the physics. i.e., they predict the same observables. Observables in quantum field theory are various things, but you can think of them as S-matrix elements, scattering, for the purposes of this. So my claim is that these two Lagrangians actually have the same S-matrices. And how do you show that? Well, the way you can think about it is that you can always calculate correlation functions by taking functional derivatives in a path integral. And in the path integral, you have an integral over d phi of stuff, right? And so I'm allowed to make a change of variable in my path integral of phi. And the claim is that by a change of variable, I can go from one theory to the other. So in this first theory, which is L1, I take phi, and I want to eliminate this term by the change of variable. And so what I'm going to do is I'm going to change phi goes to phi plus kappa phi cubed. And I claim that gets rid of this term. How do we see that? Well, if I look back up here in this kinetic term, I could have integrated by parts in the kinetic term, and then it would have looked like this. Phi partial squared phi, right? And then if I make this change of variable, well, that change of variable hits this phi as well as this phi, but both terms are going to give the same thing, so that just is canceling the half. And so this term here is becoming minus a half phi partial squared phi minus kappa phi cubed partial squared phi, and canceling off that term there. You can always integrate by parts, make the derivatives go the other way, so I'm using that. And then I have to ask, what does this change of variable do to the other terms? And that's why I carefully wrote a prime on these couplings here, because when I make the change of variable, it does change these terms. But you can see, with a little bit of effort, that it just changes the value of the coefficient in front of the operators. And you actually get a relation between the couplings in the two theories, which is non-trivial. So you better know which theory you're working with if you want to sort of compare with your friend. If you're not using the same variables, the same fields, you might have different predictions for the couplings of the theory when you compare to experiment. And sometimes there's different ways of organizing the physics that lead to relations between coupling constants in one basis or another. But in these two choices, the lambda primes here and the tau prime here are related to the lambda and the tau in the original theory by a shift that involves the kappa. So look at this term here, 2 phi's, again the half cancels, and I just shift by a kappa m squared term, but but then I get phi squared goes to phi 4, so it looks like this term. So I effectively get something that's just saying that lambda prime is equal to lambda plus that shift. That's the m squared kappa. And similar for the tau prime. Okay. Now from the point of view of the low energy theory, these are anyway just some coefficients, so it doesn't matter if I work in terms of this basis or this basis, they're just some coefficients that I might fit to experiment or determine in some other way. And so whether I use lambda or lambda prime, there's nothing bad about using the lambda prime, and it's a simpler theory. Yeah. Yeah, that's true. So there'd be kappa squared terms in this change of variable, and I drop those. And I could go through this procedure including those. And if you do the homework in the effective field theory course, you'll see what happens and why those terms work out as well. So if you want, this is all I want to say about this, but if you want more, there's a nice problem in my online course. Chapter 3 of the course is devoted to field redefinitions. And there's a problem in that chapter that's a very extensive problem. And you go through this algebra that we just did, but that's only part A, and there's B, C, D, E. And you actually show that it's true not only at tree level, which is sort of the description that we've given here, it remains true at loop level as well. So correlation functions in the two theory, S matrix elements in the two theory, will exactly work out at loop level, okay? Not just tree level, and higher point functions, etc. So it really is a true theorem. And in my online course, and if you look at some of the lectures, you also see how the proof of the theorem goes. But it's basically making a change of variable in the path integral. Yep. It's true for S matrix elements, which are evaluated on shell. Yeah. So for Green's functions, it wouldn't be true. But Green's functions aren't observable. So that's okay. It might not even be gauge invariant. Yep. Very good question. Yes. The things that you can remove, if you sort of follow how the algebra worked, are things that look like the lowest order kinetic term. So here we had a partial squared phi, and this kind of change to the variable of this very first term always induced something that looked like it, right? It has a partial squared phi in it. So there's another way of saying the results, which is less intuitive, and that is to say, and it turns out to be a true statement, that really what's going on here is that you can use the leading order equations of motion of the effective field theory, lowest order, L0, equations of motion, to simplify the higher dimension operators. So that's another way of saying it, and that sort of, in that way of saying it, you see exactly kind of what terms you're able to simplify. And the statement is that the change of variable and this statement are equivalent ways of saying the same thing. And when you go through the proof, you see why that is, but it's basically what I said, that it's always connected to the kinetic term, the change that you're making, because this is the leading term. Any other questions? Yep. Ah, very good. Yeah, so when you do the proof, you have to worry about the functional determinant. And if you look at my proof in the online course, you'll see that what happens is that you get some determinant from that. You can write that term back as an action. It's an action for a ghost. And then you work through what that ghost is, and you find out that that ghost has a mass at the high scale that you can then expand it away. And that effectively is saying that the determinant is not changing the proof. Yep. Yep.
Yeah, that's good. So part of the statement of the proof requires that the single particle states in the change of variable are unchanged. So you should have the same single particle states. So when I made this change of variable, there was a constraint on it. It could be more complicated than this. It could have some derivatives, etc. I could even shift the numerical value of this. I could put a 2 there, or I could put something else in front, some parameter. That's all fine, but it needs to have this, the quantized field needs to have the same single particle states, meaning that there should be sort of a linear term here. You could actually have a constant, that doesn't spoil anything. So spontaneous symmetry breaking doesn't spoil anything, but there better be a linear term on the right-hand side. Yeah. Okay. All right. So I want to give you an example, which is the Smeft Lagrangian, of something where dimensional counting, I want to go into Smeft in a little more detail, where this dimensional counting is kind of nice. So let's talk in more detail about this standard model as an effective field theory and think about kind of constructing it. It's very popular. It's used all the time. You'll run into it when you go to conferences, etc. So what exactly is it? Well, we should go through the steps of designing our effective field theory. And of course, this one's already been done. So I'll just tell you what the results are. For the degrees of freedom, these are just the standard model fields. Okay, QED. For the symmetries, we are going to assume some things. We're going to assume that we have unbroken Lorentz symmetry. Well, you know, that's been tested to very high precision, so let's assume that it's not broken by higher dimension operators here. We're also going to assume gauge invariance is unbroken. Standard model gauge invariance. So this is SU3 color cross SU2 weak or left-handed cross U1 of hypercharge. We're going to assume that that gauge symmetry is not broken by higher dimension operators, same gauge symmetry. You know, that's related to things like the masslessness of the photon. Of course, that's been tested to super high precision. Even the masslessness of the gluon is something that's constrained by any kind of calculations that are done with QCD. So it's also tested, and we've measured W masses and Z boson masses, and their pattern of masses is predicted by the theory. So we don't want to spoil any of that. So let's just assume this. And then the power counting is going to be operator dimensions. Okay, so the physical picture is we have this lambda nu, we have our standard model particles, which are all at some kind of weak scale. This is like top is the heaviest, but we also have the Higgs, we have W, Z, etc. They're all at this scale or lower. Includes the vacuum expectation value of the Higgs. It's also around here. And we're assuming there's no new particles in between. Any new particles have to be at least this heavy or higher. And that there's a valid expansion, that these scales here are all much smaller than that. And this was my statement earlier that M standard model divided by the scale of the new physics is a valid expansion parameter. That's our power counting parameter. So now we know that sort of we can organize things by dimensions. So Lorentz invariant theory, of course, falls under the dictates of our theorem. The zeroth order term is just what we usually call the standard model. In a quantum field theory course, that's what you study. And then we would have higher order terms, L1, L2, etc. L1 is going to be some operators that are dimension 5 divided by lambda nu. Maybe lambda nu is in the coefficients, but I'll just write it like this schematically. And this term here is going to be operators that are dimension 6 divided by lambda nu squared. And the power counting is very simple. It's just I look for the lambda nus. And so if I have a time order product of, say, an L1 and any number of L0s, but let's just take 1, that's the same size as L1 itself, because this is order 1 over lambda nu. This doesn't have any lambda nus, and this is order 1 over lambda nu, so they're the same size. As a more non-trivial example, if I take 2 L1s, then that's 2 powers of lambda nu, and that would be the same size as an L2. Okay, you get the idea. So very simple, I just count. We count the lambda nus. All right, well, in order to tell you some examples of O dimension 5 or O dimension 6, I have to tell you what the standard model fields are, or at least remind you. And so let me write down what LSM0 is. Sort of we'll all relax, it's late in the day. Maybe it's nice to see something we've seen before. So what is LSM0? By reminder, it's kind of got a lot of terms on it, but you can fit it on a coffee mug, so hey, it's not that bad. We can kind of divide the terms up into different cases. We can think of it as a gauge term, terms involving fermions. There's the Higgs sector, which is a little messier. If we want to sort of think completely, we could have a right-handed sterile neutrino, so maybe I'll add that term as well. Sterile under the gauge interactions. What is this L gauge? So remember that we're writing down things in terms of standard model fields, and this is just the standard model. So I have 3 gauge groups. I need some notation. So this is my U1 for hypercharge. This is my SU2 left, gauge bosons in the unbroken theory. And then I have the gluons in their field strength. SU3 color. And then there's theta terms, and I don't even have to write them down because you had a whole series of lectures in week 1 on theta terms, so I'll just write plus theta terms. Then there's L Fermi. In the standard model, left-handed fields and right-handed fields have different gauge interactions. So I can write down the left-handed and right-handed fermions as separate terms with some separate d's. And the d is a covariant derivative, so I d mu is I partial mu. And then there's 3 gauge groups, so there's the b mu term with a hypercharge, picks out the hypercharge of the particles. There's a G2 term with the W's, has some generator that's in SU2, and then there's a term that I just called G for the strong coupling and the gluons, and some generator in SU3. And these things act differently, in particular these two act differently on the left and right, and so that's why I separated it like this. All right, let me write down L Higgs. Okay, well there's a Higgs kinetic term with covariant derivatives. The Higgs is charged under the SU2. There's a mass term. And a phi4 term. And then there's Yukawa couplings. And of course, after spontaneous symmetry breaking, these are going to give masses to the fermions and the quarks. There's 3 different terms. And they look like this in some notation. So the Higgs is a doublet, charged Higgs, neutral Higgs. And if I take the dagger, then I get a Higgs minus, and dagger of H0. So there's some of these things are doublets under the SU2, so just let me write those. The leptons come in this doublet, and the quarks come in this doublet. And then the right-handed things are singlets under the SU2. In general, there are family indices. So I can make these into matrices and give these things indices that run 1, 2, 3. And that, accounts for the fact that I have 3 types of neutrinos, 3 types of electron, namely electron, muon, tau. 3 up quarks, 3 down quarks. So I and J are 1, 2, 3 for the 3 families. That's partly what makes, this term complicated. And you could ask, how did I figure out that what I'm writing down here? And it's really because I made things gauge invariant, right? If we go through and we think about, I'll try the colored chalk. If we think about the charges, in particular, maybe the most non-obvious one is the U1 charge, and we just go through and enumerate the charges, then they work out because I wrote down the right thing. Higgs has charge 1/2 under the U1, but Higgs dagger has charge minus 1/2. And so the sum of the U1 charges here gives 0. And it works out similarly for all the other terms. Works out like this in this term. This is minus 2/3. The right-handed ones are related to the electric charge. The left-handed ones have a shift related to electric charge. And everything adds up to 0. And here I've made an SU2 doublet, singlet by taking something that's in SU2 and something that's in SU2 and just taking H dagger L. It's kind of like H dagger H. So that's one way of contracting indices in SU2 left to get something that's a singlet. There's another way, and I've used that way in this particular term here. In SU2, I can contract 2 like things with an epsilon symbol, and that also gives a singlet. And so this epsilon in as a matrix would be like 0, 1, minus 1, 0. It's an antisymmetric combination of these 2 things, and that's a way of getting a singlet. Okay, plus Hermitian conjugate, which should be there somewhere. For the last 3, which aren't Hermitian. Okay, so that's the standard model. I won't write down the right-handed neutrino. There's a problem in the course that writes down the right-handed neutrino Lagrangian in chapter 2 if you want to see it. So let me check what time it is. 4:08. So I should finish up in the not too distant future. Let me give you some examples to close off today's lecture of higher dimension operators that are in this standard model. This is L0. What about L1? What about L2? So dimensions greater than 4. That's the fun part. This is something that you've seen before, probably. So it turns out if you go to dimension 5, that there's only one type of operator. Amazing. You go through all the gauge constraints from the gauge symmetry and Lorentz invariance, and just it eliminates everything except for one term. And the one term that survives is actually very interesting. It involves kind of the combination of the Higgs and the left-handed doublet that wasn't appearing here. Like here I had H dagger left LL, and then I balanced with ER. Now I'm balancing the hypercharges just directly, minus 1/2 and plus 1/2, by putting them in at the sort of the same level. And this epsilon is kind of the same as this epsilon up here, putting the SU2 doublets together with an epsilon. So that's perfectly allowed. This LL conjugate is just some notation that means LL transpose times a charge conjugation matrix, where C in some standard representation is just I gamma 2 gamma 0. And basically what this is doing is it's putting the, if you look at the fermion indices, right, to not spoil Lorentz invariance, I have to have a Lorentz invariant in the fermion indices, in the spinor indices, and this LL is contracted with this LL through this thing that's also effectively an epsilon, but in the spinor indices. And that's a way of making a singlet in spin. And so this thing is Lorentz invariant because of the C. And so it's sort of contracted both in the SU2 for the left-handed gauge as well as in the spin with an epsilon. And you could try other things and none of them will work. I leave that as homework. Now this term is very interesting because this term is giving actually some physics predictions if you sort of think about what physically it can do. And that's because in this theory that we set up, we have spontaneous symmetry breaking. I mean, spontaneous symmetry breaking happened in L0. Higgs gets a vacuum expectation value. Symmetry is broken by the choice of the ground state. That's what spontaneous symmetry breaking means. We expand around the new ground state. The Higgs can be replaced by a VEV. And if we replace the Higgs by a VEV in this term, then what happens is it gives a mass to parts of LL. And if you work out what parts, just because you're replacing Higgs by 0 kind of V, where V is the neutral Higgs, you don't want to break charge. So you have to give the neutral Higgs a VEV. This gives a Majorana mass to the neutrino. So the lowest dimension operator in this SMEFT EFT gives a term that looks like this. These are spinor indices A and B, and there's an epsilon symbol. When I stick in the VEV, that's the type of operator I get. And this M nu is just related to the coefficient in front and sticking 2 V's in for the H. So the M nu is C5 lambda nu times V squared. And so the neutrino mass, Majorana mass, that I predict from this procedure is naturally small because it was a higher dimension operator. Exactly how small? Well, it's kind of the biggest scale in the standard model, V squared divided by lambda nu squared. Sometimes this is called the seesaw mechanism. It's usually called that in the context of thinking of the new physics. Lambda nu is coming from a right-handed neutrino that was heavy. If I integrate out the right-handed neutrino, I will generate a term like this. And then sort of the lambda nu is like the right-handed neutrino mass. If you want to see how it works in that context, this problem I mentioned in chapter 2 where the right-handed neutrino Lagrangian is written down, that problem goes through that math or forces you to go through that math and see how you would generate an operator like this from integrating out a right-handed neutrino that's heavy. But from the point of view of the effective theory, we just say, look, this is very natural that there could be a Majorana mass term for the neutrino because it's the lowest dimension operator in SMEFT. Of course, the constraints are pretty strong and they actually force this lambda nu to be pretty big. So M nu being less than half an electron volt implies lambda nu to be greater than 6 times 10 to the 14 GeV. So it's a pretty big scale. Certainly not something we've probed directly in colliders. But it's still natural that there could exist a Majorana mass term just from this mechanism. Of course, we don't know if it's the dominant thing, but this sort of says that it's kind of natural if it's there. Okay, let me give you one more example before we quit. So that's the only thing that happens at dimension 5. At dimension 6, there's many more terms. So at dimension 6, there's a whole sum of coefficients and operators. And the sum can be written, if I ignore flavor, as going from 1 to 59. So there's 59 different operators. But these 59 operators are describing physics across the whole standard model. So it's like if you pick a particular thing in the standard model and you say, I'm going to focus on this, only a handful of them are going to contribute. And so just to give you an example of that, if I look at dimension 6 and I ask about the muon magnetic moment, okay, this is G minus 2 of the muon. I can ask, if I look at this operator basis, I can ask kind of which terms in that operator basis can generate a magnetic moment for the muon. And I can go through and I can identify the ones that do that, so I'll just write those down for you. There's 2 of them. So again, has to be a gauge singlet, has to be Lorentz invariant, and it has to connect to muons and a photon. Well, the photon is a linear combination of the W and the B, and so I can have an operator with either a W or a B. And so these are the 2 operators that would generate some diagram like this. And it has, with this sigma mu nu, it's actually a magnetic moment for the muon. And so what these operators are doing is giving you some formula that's saying the total magnetic moment is sort of the magnetic moment from the standard model Lagrangian at 0th order. So all the radiative corrections and loop corrections that contribute in the standard model to G minus 2, plus some tree level contribution, which comes with some coefficients of these operators, I'll just call C. And it comes with at lowest order, the Higgs can be replaced by a V again. And then these are dimension 6, so there's 2 powers of lambda nu. And to make it dimensionless, I just stick in the most important standard model scale, which is the mass of the muon. And I can characterize that, how big this effect is. If I say these are order 1, then I can figure out how big this has to be to agree with the experiment, right? And I can play this game for various things in the standard model, figuring out that there's higher dimension operators, there's some number of them, there's some set of coefficients, and any new physics model that I might think about considering at low energies is just going to be represented by the physics inside these operators. So the only thing that can differ is sort of the value of the coefficients of those operators. Okay, I think I had one more example, but it's fine. I'll maybe cover it at the beginning of next lecture. I think it's a good place to stop. And I'll take more questions. Any final questions before we end the day? Or you can save your, okay, go ahead. Yeah. Yeah, good question. Yeah, so it could not be order 1, right? In some new physics model, maybe it's small. Really what you're constraining, like oftentimes people write it the way I wrote, really what you're always constraining is C5 divided by lambda nu, right? That's kind of like, if I said that, then you wouldn't have a question. But, if the sort of physics of the higher dimensions is natural and just order 1, then all the sort of numbers are contained in the scale lambda. If this is like 10 to the minus 5, there's probably a reason, right? So it's sort of another question. But really, you're right. You're really only constraining the ratio, lambda nu divided by C5. That's right. There was another question. Yep. Yeah, it's pretty strong. I don't remember the exact number. I think in my online course I write down the exact number, but I didn't write it down. But it's, multi-TV, if I remember correctly, like 20 TV, something like that. Yep. Yeah. Yeah. Yeah, so not quite that, but like it's related to what you said, is that you're not really sensitive to off-shell terms. Now, you have to be very careful with that statement, because when you have propagators in some intermediate states, even in a tree level diagram, they're off-shell, right? So really the only thing on shell is the external particles. But nevertheless, this term that I had with the partial squared phi, phi times phi cubed, if you'd make predictions in that theory and you just forget about what I said and you said, I'm going to include that operator, I don't believe Iain's right about that proof. What you'll find is that all your predictions are giving the linear combinations that I identified. You'll always find those linear combinations showing up in all your predictions, no matter what you calculate, if you do the calculation right. So that's sort of and so in that sense, the operator is redundant. It's kind of like a flat direction. And you can imagine, if you're doing some fits in this standard model effective field theory and you kind of had too many operators, you had some redundancy, but like maybe the formulas are so complicated that you didn't know, and then you started to try to treat those parameters as independent, you'd have like some runaway directions. So it would be very important to eliminate operators that are not needed, that are redundant in that sense. And that's what's been done in this like enumeration up to 59. Like there's a whole bunch of operators that could have been there, but you eliminated them with the equation of motion to get to a minimal set. And the 59, by the way, doesn't count flavor indices, which makes the number much bigger. Yep. Yeah. Good question. Yeah. That's a good question. I actually don't know the answer. I suspect that the answer is that it doesn't, because it's hard to, experimentally verify the z's, the zns in the standard model, but I actually don't know for sure. It's a very good question. Interesting.